This is our final project video for ND106. I'm Nathaniel.
Hello, my name is Gagan.
Hi, my name is Harwinder.
Our project is an automatic sit and stand chair. The purpose of the project was to provide more comfort and convenience for the physically disabled and elderly in the action of sitting down and standing back up from a chair. The chair raises from a seated position to a more inclined position, such that it's easier for them to move in and out of the chair, and reduces the difficulty of this everyday task, ultimately providing them independence by not having the need for any external help and improving their quality of life. Next slide. For design specifications, the chair prototype that we had made is a 1/4 scale of a dining chair that we had measured. The dimensions of the chair in SolidWorks came out to be 5.75 by 7 by 10.6, which is nearly identical to the actual chair dimensions when it was assembled. The chair starts off at a 0-degree angle with the seat parallel to the floor and extends upward of a max angle of 55 degrees. The linear actuator chosen can carry up to 4.5 pounds each. This is quite low, but for the purposes of this project and because of budget restrictions, it was sufficient. The time for the prototype to go from a seated position to a standing position takes 3 seconds total, but this can be adjusted easily by adjusting the voltage supply from the drop booster. Next slide. For the electronic components, we have here to the left
The sensor.
There's the chair on top of the seat. On top of the seat is the capacitive touch sensor. At the bottom of the seat, we have the ultrasonic distance sensor facing the front. Those are the two linear actuators. We have an LCD interface that would be installed on the armrest of the chair. You can also see there the Raspberry Pi Pico connected to a breadboard controlling the whole system. And there's an H-bridge controlling the two linear actuators. And lastly, a drop booster, providing our specific voltage to the system. For the wood components, we use a total of 4 hardwood squares, each 3/4 by 3/4 by 4. A 2x2 plywood sheet with a thickness of 1/4. And the joints that allow the seat to pivot is a 5/16 by 1 1/2 screw with posts. And to connect the bottom structure together, we use two 1.5 inch corner brace. The total cost of the project came out to be $123.48. Next slide.
Here's the diagram for our schematic. As you can see, we are using an H-bridge to control both of the linear actuators. Our system is being powered by the Drock power supply at 12 volts. The Pico pins GP6, 7, and 8 are used to control one of the linear actuators, and pins GP10, 11, and 12 are used to control the other linear actuator. Our system includes an OLED display, which is powered by the 3v3 pin and connected to GP16 and GP17 on the Pico. We also have an ultrasonic distance sensor, which is also powered by the 3v3 pin, and its signal and NC pins are connected to GP1 and GP2. Lastly, we have a capacitive touch sensor, which is also powered by the 3v3 pin. Its I/O pin is connected to GP18. All of the grounds are connected to a common ground on the breadboard. So next, I will explain to you a little bit of how our code works. The code begins by importing the necessary modules. Then it defines all of the pins and initializes the ultrasonic distance sensor, capacitive touch sensor, motor driver module, and OLED display. Next, we define multiple functions for controlling the display, for moving the linear actuators up, moving them down, and making them hold position. The code is run in a while loop. It continuously measures the distance of the user and whether or not they are seated in the chair. When the user gets within 140 millimeters of range of the seat, the move up function takes place by moving the linear actuators up. Once the user's bottom makes contact with the capacitive touch sensor, the move down function starts to move the linear actuators down. Then the code waits for the GP20 button to be pressed. Once it is pressed, the seat continues to rise until the user's bottom loses contact with the capacitive touch sensor. Then the hold position function takes place, holding the linear actuators for 5 seconds before moving down. The code then waits for the user to come back within range once again.
So this is how our project works. When an individual walks up to the seat will rise. And when the individual's bottom touches the seat will go back down to a seated position. When they're ready to get off the seat, all they have to do is press the button and the seat will rise once again. After about 5 seconds, the seat will go back down to its seated position. We'll show that one more time. Another nice feature about the seat is that if the individual wishes to be seated before the seat rises to its full 55-degree angle, the seat will start going down as soon as their bottom touches the seat. This is also the same way for when the individual wishes to get off the seat. Whenever the user's bottom gets off the seat will stop at the exact spot and wait 5 seconds, then go back to its seated position. Show one more time here.
So for individual tasks and what was learned, I'm Nathaniel, and I was tasked with a design lead. But overall, it was a collaborative effort of researching existing designs for sit and stand wheelchairs. We then drew inspiration from them and learned and took notes of their features and mechanisms. After that, I created an initial model using SolidWorks. We were initially having trouble for the backrest of the seat. When designing it, we wanted it to straighten all the time while the seat changes position. But through an iterative design process, it adjusted dimensions of the 4-bar mechanism and made necessary modifications to cater to the dimensions that we had wanted and the dimensions that we had bought. Throughout this process, we gained valuable knowledge about the mechanism design, SolidWorks, fabrication techniques, and also coding and understanding the functionality of the 2 sensors that we had used, which were the ultrasonic distance sensor and the touch sensor.
I'm Harwinder, and I was the fabrication process lead. From the fabrication part of this project, we learned many different things. One of the things that we learned were technical skills, as we had to work with various tools, equipment, and materials. With the hands-on experience, we learned and improved our skills on how to operate specific machinery as well. These technical skills can be applied to our future projects and help us become more proficient in the fabrication process. Another thing we learned from the fabrication part was the safety protocols. When we made the cuts for the square dowels and plywood, we had to use potentially hazardous machines, including the miter saw and table saw. We made sure when we used these machines that we had our safety glasses on, no long sleeves, and nothing on our wrist. This knowledge ensures a safe working environment and can be carried over for future projects.
I'm Gagan, and I was the lead of the coding aspects of the project. So when we were writing the code for our project, we found it difficult to integrate all the sensors and controllers to work together to perform a series of functions on their own without interfering with each other. In this process, we learned that it is best to take it one by one and program each sensor individually before tying them all together. We also learned that if you get creative with the while, if, and else loops, it's possible to shorten down the code significantly.
Automatic sit and stand chair. I'm Harwinder. The project was to provide more comfort for students with a physically disabled, elderly, and option of sitting down considered by government. Chair original material was situated such that it's easy for the view looking out of the chair and reduces the difficulty of the So this is an H bridge. It's built with an actuator. Good. So this is how the chair works. When a person is ready to sit in the chair, it's pretty open. Sit down. Walk into the chair. Sit down. The chair will take down. When you're ready, all the putting weight on that, having weight on that, and pressing that on.
Yeah.
Okay. And what's the condition to come back?
So when the chair or when the user gets off the chair and is ready to go back on it,
Basically, the weight feels like low, yeah, the weight is and then the other also starts to also take something goes together with the
I'll show it one more time.
yeah, if you press that, still keep apply some pressure on it. It will come back or it will. If you bring it down, but ultrasound doesn't detect anything. But there is a pressure on there. Can you bring it down? Still have some weight. Come back. So it's in the space on ultrasound. I mean, usage of things. This one. I don't know, but press it to go. Otherwise, it will go down.
Then you just want it to start going down before the user is ready to
It should go up.
before you rise all the way up, it knows to go back down. Yeah. It doesn't have to come all the way up.
Got it. Okay.
Also, if the user wishes to get off before it goes to the maxing, so it stops. So it stops whenever the user gets off the chair.
Got it. Okay, thank you guys.
So this is the end to our project video. Thank you very much.